Now let's talk about something called uh, dealing with uncertainty. So when we deal with the numbers in the real world, we're going to deal or dealing with uncertainty. What does that mean? That means that's not 100% accurate, or it's not very sure, right? So let me give you a quick example, then you're going to get some basic understanding about what we're going to learn. All right, a young man get a job in a museum, and they have like a whole exhibition about the Earth. All right, so when he get in, and then he found that the Earth, our Earth, is 4.6 billions 4.6 billion years old. Okay, that's what his boss, or it was written at the board next to the picture of an Earth, of our Earth. And then there's another one said the universe. The universe is 13.8 billion years old. Oh no, let's write what is a 4.6 billion. So that will be 4.6 and 0.00000. So that's pretty big number. So that's a unit, tens, hundred, thousand, million, billion. So that is this many years old for the years old. All right. Okay. Now, this guy worked in the museum for 3 years, and at the year 3, he will introduce something to a group of students. So what he said is the Earth is 4.6 billion and 3 years old. You know where that 3 comes from? So he did this, right? He just simply just plus 3. That's 3 years he has been working in this museum. So he said the Earth is 4.6 billion and 3 years old, and the universe is 13.8 billion and 3 years old. Does it sound right? Can you get this conclusion? Well, you might want to think about that, because sometimes when we talk about something really, really big, and this minor thing doesn't count, isn't it? So the 3 years that he had been working in this museum will not be counted into the lifetime of the Earth and the universe. Okay, so we're going to talk about something important. It's called significant digit. That is a very important concept. So every time when I ask you how many significant digits, you should be able to tell me. All right, now there's following rules you got to know. First of all, when we talk about like a time, let's say 11.9 seconds. Okay, that's how long it takes this guy finish a 100-meter dash. And then this one has 3 significant digits. 119. So what does that mean? That means non-zero digits. They are significant. Okay, non-zero digits, they're always significant. Now let me give you another example. 11.90 seconds. Then how many significant digits? Guess what? 4. 1 and a 1 and a 9 and a 0. So this one has a 4 significant digits. Why that 0 is also a significant digit? I think usually when you were at like elementary school maybe, and the teacher might tell you, oh, the zero, there's a decimal point. So 11.9 and 11.90, they're the same, and this zero doesn't count. She's right. In the absolute value, when we talk about the value, yes, they don't. But when we talk about significant digits, this one is a very, 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 very important. Okay, I will talk about this later. You're going to see why this zero makes a big difference. Okay, so zeros that follow a non-zero digit and to the right of the decimal point are always significant. So at the end, this is significant. Significant. Okay, that's to the right of the decimal point, but followed by a non-zero number. So that's significant. All right. Now let me give you another example. What about this one? When we talk about a dollar, 204.99. How many significant digits? 5. All right. You might say, wait, there's a zero here. Yeah, but this zero is in the middle, so it's also counted as significant. So even, do you remember? This is significant. Do you remember we just said earlier, we said, well, all the non-zero digits is significant. And the zero between those non-zero numbers, they are also significant. Okay, so that's 5. That's 5 significant numbers, 5 significant digits. Okay, now the next one. 0.00030. It's a little tricky, right? How many significant digits? Guess what? 2. There are 2 significant digits. There's a 3 and a 0. So 0 to the left of the first non-zero digit are never significant. Okay, so to even is behind the decimal point, but this is if you go from the left, and this 3 is the first non-zero number, so your significant digit starting from here. And do you remember the 0 behind a non-zero number, which our second example, and that 0 is also significant. So there are 2 significant digits. Okay, it's tricky, isn't it? All right, now the next one. What about this one? 240,000. How many significant digits? Here is actually the decimal point. There's nothing behind, but before that they have a 0, 0, 0, 0. This one has 2 significant digits. So it says 0 to the right of the last non-zero digit. All the zeros to the right of this 4, but before the decimal point are not significant until stated otherwise. So most of the time, if I didn't say anything, then you have only 2 significant digits. All right, so that's pretty much covered up like a lot of rules we need to know. All right, now let me ask you another one. 1 mile equals 1.609 kilometers. We learned this already, right? What about a 1 square mile? 1 mile square. That would be 1.609 kilometer times 1.609 kilometer. Then I ask you to convert 1 square mile into the square kilometers, but I ask you to give me your answer with 3 significant digits. I need the answer with 3 significant digits. How would you do that? So 1.609 times 1.609. If you use a calculator, you're going to see the number, which is 2.5881 kilometer square kilometers. So I need 3 significant digits. 2.5, I'm going to round this one. So 2.5881 2.59 square kilometer. That is your answer. So that's you give me your answer with 3 significant digits. Okay, now you see what we're doing here, right? I want to keep this 2, that's the first significant digit, and the 5. And I want to have the third one. I don't want anything after this, but however, this digit is 8. What did I do? I round this 8 up to 9. So I round it up. Okay, now let's talk about rounding. You see this a lot, rounding. Excuse me, we learn significant digits. Now we're going to learn rounding. First of all, let me give you a big number, okay? I give you 6,192.58842. This is the number. And I ask you to round this to the nearest, all right, now to the nearest what? To the nearest 1,000. To the nearest 1,000, 100, 10, 1, 10th, 100th, and 1,000. I think after you learn this, you should be okay. All right, how should we do that? If I ask you to round it to the nearest 1,000, 1,000 is this digit. So you know this is the decimal point. To the left of it is called a unit or ones, tens, 100, 1,000. So that's here. We need to round this number. We need to round this number to the nearest. Did you see that? We round it to the nearest. It's not accurate. It's not super accurate, but it's very close, and we only want that in thousands. So if you round it, you always look at the one number next to it, to the right of it. If it's 0, 1, 2, 3, 4, you just drop it. If it's 5, 6, 7, 8, 9, then you just round it up. So in this case, here is 1,000. Therefore, we get that. And the next one is 1. Of course, it's going to be gone. So the answer is this. Okay. So if you round it to the nearest 1,000, it's going to be like this. What about rounded to the nearest 100? Here is the 100 digit. And then the next to it is a 10. And this is 9. So I have to round it up. So I'm going to get a 6 to 100. Okay. So I rounded up to 6,200. And very similar, I rounded to the nearest tens, so which is 2 here. So that's going to be 6,190. All right, and rounded to the ones, which is this 2. We're going to stop here. So we look at the digit to the right of it, which is 5. So that goes up. So 6,193. All right, now when you get here, you might say, oh, this is the exact value. And this, when you round it to 1,000, then that's a 6,000. That is why when we talk about the Earth is 4.6 billion years old, we talk about like 100 million. We round it to the nearest 100 million, isn't it? So that's why there's still some numbers behind it, and we just ignore them, okay? So we round it. Right, now that's why you cannot add 3 years to the life of the Earth and the universe. Now 10th, which is here, 5. You look at the next digit, which is 8, so you round it up, which is greater than 5, right? So it's a 6,192.6. Got the answer? All right, now hundreds, which is here. So that's going to be 6,192.59. And the very last one, thousands, is going to be 6,192.58. Here's a 4, so it'll be gone, and then that's 8. So that's your answer. Now, if you look at this, you're going to see how do we round a exact value to the nearest. I tell you to what level you're going to round it. All right. So that's when you round. That's how you do it. Okay. The last one is When we round, I told you that when we round it, there's some error, isn't it? We have some rounding error. So the rounding, we talk about the errors. And then we have two types of errors. One is called a random error. The other one is called a systematic error. Systematic error. What is the difference between these two? Random error and a system error. Let me give you a quick example. If you are going to measure the weight of a person, so you have a scale, right? You let this person stand here, and then here you're going to read like this person is, for example, 150 pounds or something like that. All right, so that's what you're going to do. If you just go there and sometimes slightly higher, slightly lower, then this is not super accurate, and that might be the random error. Or I might have a different scale, right? You go each one, and then you might have a random error there. However, if this scale is always like 2 pounds more, even you put nothing there, it still shows 2 pounds. So everybody step on it. For example, this person is 150 pounds, but the little meter will show you 152. That's not right, right? There's 2 pounds. That's the error. And then the next person who is 110 pounds, but the meter shows 112. So again, there's 2 pounds. That was the error. That is called a systematic error. So that occurs, the systematic error occurs when there is a problem in the measurement system that affects all measurements in the same way. That's called a systematic error. Okay, but a random error was it occurs because of a random or inherently unpredictable events in the measurement process. Like someone just go there, roughly take a look. He didn't pay attention, then he just write down 156. That is a random error. It doesn't happen to every single person when they take the weight. You get the general idea about this? It's a random error and a systematic error. And there's another thing. It's called there's another type, two kinds of error. We call that absolute error and a relative error. Okay, absolute and a relative. Sounds very familiar, right? So the absolute error is the measured value minus the true value. That's the absolute error. So for systematic error, then we're going to always see, the measured value and the true value is always 2. So when there's a consistent absolute error, most likely you're going to see that's a systematic error. All right, so this is the value minus value. When we talk about pounds, or when we talk about dollars, or when we talk about centimeters or square meters, things like that, and we talk about absolute error. So that error and the difference and the measurement itself has the same unit. Okay, so if your true weight, for example, this is you, and the true weight is 125 pounds. All right, and the measured weight is 130. I tell you that you're 5 pounds more, but you know it, but other people don't know, right? So what is the absolute error? The absolute error will be 130 minus 125. The measured minus the true. So the absolute, this one, the absolute error, measured value minus true value, which will be 130 pounds. 130 minus 125 pounds. So the answer is 5 pounds. That's your absolute error. All right, now what is a relative error? Relative error is this one, that equals the absolute error divided by the true value. Okay, so it's a ratio. It's a ratio. Sometimes we use a percent to show it. For example, in this case, our absolute error is 5 pounds. What is the relative error? Which is this 5 pounds compared with the 125 true value. So now it's going to be 5 pounds over 125. All right, and that is 0.04 or 4%. This is the absolute. Sorry, this is absolute. This is relative error. This is the absolute. Okay. Now you see the difference? The absolute, we talk about the value minus value, and the relative error, we talk about the percentage. Okay. And the last concepts that you're going to you should be able to tell the difference is accuracy and precision. So accuracy versus precision. Okay. What does that mean? What's the difference? Is this accurate? Is this precise? If you just think about that, well, it sounds very, very close, right? Actually, this accuracy describes how close the measure value is to the true value. All right. So if your weight is 125, but the scale 1, okay. Again, this person, 125 pounds. All right. Now, I have 2 scales. They always have like a reading meter. Okay, I will let this person, so this is a scale 1. This is a scale 2. All right. Now, I let this little person stand on here. And then I'm going to see this one. This one shows 126. It shows 126 pounds. All right. And this one shows 126.3 pounds. I ask you to think about this. Both are not right. Your actual weight is 125 pounds, but when you stand on this, the little meter show you 126. Is that accurate? No, it's not. And what's the difference? Or what is the absolute error? 1 pound, isn't it? Okay. And what about this one? You stand on this, and the meter showed that your weight is 126.3 pounds. What is the absolute error right now? That will be the difference between these two. So it's going to be 1.3 pounds. Which one is more accurate? This is more accurate because the error is smaller. The absolute error is smaller. So this one is more accurate. However, this one, did you notice this one give you to the 10th, which is 1 decimal point, decimal places here, and this one just stay at the integer. So this one is more precise. This one is more accurate. To compare that, you're going to see which one give you the smaller. The accuracy means close to the true value. Precise means the amount of detail in measurement. So this one goes to 10th, so this one has more detail. Therefore, the scale 2 is more precise than scale 1, but scale 1 is more accurate. You see the difference between these two? So don't be tricked when you say something was precise, and no. And this precision is just talk about the detail. Can they go to the detail? Okay, we go back to the very, very early time. Okay, the Earth is 4.6 billion years old, and that is this a precise value? I guess not, right? Because there's going to be a lot of numbers or digits. They're not zero. It's go behind. So this is not very precise. All right. Is this accurate? I don't know. Maybe someone comes with like a 4.68, Okay, that is more precise, but it might not be exactly, I don't know which one is more accurate because I don't really know the true value. All right, now quickly review. This is what we did today. Dealing with uncertainty. That means in the real life, in the real world, you're gonna see a lot of numbers. It's not accurate. It's not the real value by itself. So you're gonna understand it. First of all, you have to know. You have to tell me how many significant digits. If I write a number, if I give you 1.5, you have to say 3, okay? And this 1.90, you're gonna give me 4, things like that. So I'm gonna test you this for sure. So make sure that you go over this again, and write some numbers or work on the homework to make sure that you can identify exactly how many significant digit a number shows. All right, and then the second, of course, when I give you a number and I ask you to give me the answer with 5 significant digits, you should be able to know how to do it, or 3. And then we talk about the rounding. We round to the which place, then you should know this. I think a lot of people know this already. So after rounding, and then we talk about some error, because every time when we round, we made some error, right? Make some mistake. It's not going to be exactly the same as the original value. So we talk about what is a random error, what is a systematic error, okay? And we talk about what is the absolute error, what is the relative error. We also talks about the difference between the accuracy and the precision. So if you know all those concepts, you pretty much know what I want you to know in this session when we deal with the numbers in the real world. How do we deal with uncertainty?